Welcome to The Explainer. I am so incredibly thrilled you're joining us today because we are diving into a really fascinating piece of research. We're going to explore a topic that sits right at the intersection of everyday logistics, highly complex discrete math, and cutting-edge quantum physics. Honestly, it sounds like straight-up science fiction, but it's very real, and it's currently being used to solve massive problems that our standard classical computers really struggle with.
Okay, picture a real-world logistical nightmare for a second. You have a massive, rapidly growing fleet of electric vehicles. Let's base this on actual public charging network data from Paris. Now, all these users pre-book their charging times. Your job is to schedule every single one of these cars to charge without their times overlapping, all while minimizing the total number of physical charging terminals you actually have to build and maintain. So how do you pull that off? It sounds like a pretty basic scheduling task, right? But as the number of cars scales up, it very quickly turns into a seemingly impossible puzzle. Okay, let's dive into this roadmap. We'll start with the smart charging puzzle. Figure out what graph coloring actually is. Introduce Gaussian Boson sampling. Translate all that math over to quantum. And finally, look at the quantum versus classical results.
Starting off with Section 1, the smart charging puzzle.
To really ground this in a tangible problem, let's look at the raw constraints of assigning our EVs to terminals. Each car has a strict, pre-booked charging interval. You absolutely cannot have overlapping times on the exact same terminal, and your main goal is to minimize the total number of terminals you're using. Well, in computer science, this whole headache is known as the interval scheduling problem, or more specifically, the group interval scheduling problem. And here's the catch. For complex groupings, this is actually a famously unsolvable math puzzle in disguise. It belongs to a class of problems called NP-hard. Basically, that just means as you add more cars, the computing power needed to find the perfect schedule literally explodes exponentially.
Moving right along to Section 2, what is graph coloring?
We really need to translate this real-world headache into a mathematical framework that a computer, or, a quantum device, can actually process. The framework we use here is called graph coloring. By definition, graph coloring is just the assignment of labels, which we call colors, to each vertex of a graph so that no two adjacent vertices share the exact same color. Let's apply this back to our EV scenario. Think of every single EV charging request as a dot, or a vertex, on a graph. If two EV charging times overlap, they're incompatible, so we draw a line, or an edge, connecting them. The colors in this case represent our physical charging terminals. So the rule, no two adjacent vertices share the same color, simply means no two overlapping EVs can be plugged into the exact same terminal. The entire goal is to color the whole graph using the absolute fewest colors possible.
And this brilliantly illustrates exactly how researchers manipulate this graph to solve the problem. To figure out if a graph can be colored with, say, K colors, they create what's called an augmented K graph. They literally make exact copies of the vertices for every single possible color. Then, they add conflict edges to represent overlapping times, and clonal edges just to make sure one EV doesn't accidentally get assigned to two different terminals. Finally, they completely flip it to create a complement graph. In this flipped version, the impossible scheduling problem becomes a hunt for something called a clique, which is basically a perfectly interconnected, dense cluster of vertices. Find the largest clique, and boom, you've found your optimal charging schedule.
Which brings us to Section 3. Enter Gaussian Boson Sampling.
So how on earth do we find these cliques efficiently? Enter Gaussian Boson Sampling, or GBS for short. This is a photonic quantum computational model. Instead of relying on traditional silicon microchips, GBS uses linear optics. It fires single photon states through this crazy network of beam splitters and phase shifters. Now, in traditional computing, randomness is usually a huge problem. But GBS actually leans into the intrinsic randomness of quantum mechanics. It uses it as a super powerful tool to solve sampling problems that would honestly take a classical supercomputer thousands of years to crack.
Here's the absolute game changer with GBS. It naturally finds dense subgraphs with high probability. Because of the wildly complex math happening at the quantum level, the photons just naturally group themselves into patterns that represent highly connected networks in our graph. And remember what we're looking for: cliques. A clique is essentially the ultimate dense subgraph. So GBS acts like a massive quantum spotlight, instantly highlighting the absolute densest parts of the graph where our optimal scheduling solutions are hiding out.
All right, Section 4. Translating math to quantum.
Let's see how this all builds together. We have our graph coloring math, and we have our quantum photonic spotlight. So how do we actually combine them? Well, this is the iterative loop of the new GBSC, or Gaussian Boson Sampling coloring algorithm.
It doesn't try to solve the entire massive graph all at once. No way. It takes the uncolored graph, transforms it into that augmented complement graph we talked about earlier, and then uses the quantum GBS process to find a really massive clique. That clique gives us the perfect coloring for a large chunk of the graph. From there, the algorithm simply grabs the leftover uncolored vertices and runs the entire loop again and again until every single EV is perfectly scheduled.
Breaking that down into steps, the algorithm first builds the augmented K-graph to map out all the constraints. Second, it creates the complement graph. Third, it uses the immense quantum power of GBS to sample those dense subgraphs. But, quantum devices give probabilistic results, so step 4 is a classical cleanup heuristic called shrink and search. Think of it like pruning a bonsai tree. It takes the dense subgraph found by the quantum device, trims away the loose edges, and swaps vertices in and out to grow it into the absolute maximum clique possible. It's just this beautiful hybrid mix of quantum intuition and classical refinement.
Finally, Section 5, Quantum versus Classical Results.
So how does this hybrid quantum-inspired algorithm actually hold up against the best classical methods we've relied on for decades? In the classical corner, we have absolute heavyweights like de Sitter, RLF, and SLI. These are sequential coloring methods. De Sitter, for instance, prioritizes coloring the vertex with the highest degree of saturation, meaning it looks for the EV that has the absolute most scheduling conflicts and tries to handle that nightmare first. They are smart, logical, step-by-step algorithms. But in the quantum corner, we have our GBSC algorithm, which uses global quantum sampling to find massive solutions all at once.
I really want you to focus on this number, 24. In the comprehensive tests running the Parisian EV smart charging use case, GBSC went head-to-head with the de Sitter algorithm across 24 different chromatic classes. And the final score? GBSC won 24 times. 0 draws, 0 losses. An absolutely flawless, undefeated shutout against a highly respected classical heuristic. So the crucial point is really clear when you look at the full breakdown. Against DACIT, a complete 24-0 sweep. Against RLF, GBSC won 18 times, drew 5, and only lost once. SLI definitely put up the strongest fight, but GBSC still came out on top with 9 wins, 9 draws, and 6 losses. And what the researchers noted was so fascinating. As the graph density increased, meaning the scheduling conflicts became way more tightly packed and complex, the GBSC algorithm dominantly outperformed its classical competitors even more.
Let's summarize the big takeaways here. The quantum-inspired GBSC consistently achieved the lowest average excess colors overall. In the real world, that translates directly to needing to build fewer physical EV charging terminals. It showed exceptional performance specifically on dense graphs, which are notoriously the absolute most difficult networks to color. And the algorithm proved its worth not just on theoretical Erdos-Rainy random math graphs, but it strictly optimized the very real Parisian EV charging data we talked about at the beginning of this explainer.
Now I want to leave you with a final, kind of mind-blowing thought. Everything we just looked at, these incredible dominating results were actually achieved on high-performance classical supercomputer clusters that were just simulating the quantum behavior of GBS using the Strawberry Fields library. They were simulating the quantum world because real physical photonic quantum computers are still in their infancy, dealing with photon loss and scaling issues. So, if mere classical simulations of these quantum algorithms are already this incredibly powerful and efficient at solving our worst logistical nightmares, what happens in the near future when the actual physical photonic hardware fully scales up? The possibilities for optimization are truly limitless. Thanks so much.